So I would like to thank the organizers for giving me this opportunity. So I'll be talking on basically what's called as breadth figures. Okay, breadth figures is nothing but okay. So this is basically work done with Ardeen Array, Arun Banpurkar, and Nilesh Pawar.
Can you turn on your video, please?
You want?
Yes, please. Thank you.
Okay, so basically the work is done with some of my PhD mates under the guidance of our PhD guide A.V. Limay. So Ardeen Array, he has done a lot of work with experimental work on these breadth figures. Okay, so breadth figures. Okay, breadth figures are basically droplet patterns when there is a condensation of vapor on cold substrate. So the most familiar example is when we see water droplets getting condensed on any cold substrate. Then there are three regimes. Initially, there is a nucleation, and the droplets are isolated, so they grow due to direct absorption from the above when vapor is directly condensing. Okay, then there is intermediate or crossover stage. Means some of the droplets, they grow a bit larger, and then they coalesce and they form a bit bigger droplet. Okay, but here vapor is condensing plus few events of coalescence, and then finally this thing enters in what is called as coalescence dominated state. So a lot of coalescing events are taking place. Okay, so they have these own features. Here is a picture on the right hand side. This is a molten tin droplets condense on sapphire Al2O3. So the quantity of interest for this particular analysis of patterns is basically average droplet size. Okay, so initially all droplets, when they are nucleated, they are of same size. And then when they coalesce or they are growing because of condensation of vapor directly plus coalescence. Okay, so there are many sizes of droplets. Then droplets have distribution, and then area coverage. So area goes on, coverage goes on initially increasing, and then it goes to maximum, and then it saturates. Okay, then there are few parameters here. Means what type of substrate is there. So it can be a solid substrate, liquid substrate. Okay, liquid substrate are quite interesting studies because liquid surface is quite moving. Then temperature, at what temperature this is happening. Then substrate features. Substrate is solid. In solid, whether it is smooth, pattern, if it is inclined. In liquid, again, it's normal liquid or liquid surface. If liquid is volatile, then surface is having very rigorous activities. Okay, then what is the mechanism of vapor delivery? Whether it is continuous or pulse. Pulse means just the pictures you are showing. These pictures of tin, they are grown using pulse laser deposition. And then droplet kinetics, whether droplets are static when they get deposited or they keep moving, means whether diffusing or even they jump. Okay, so so initial stage, what is observed is initial stage, droplet radius goes as T⁻⁴. Okay, then during intermediate or crossover stage, surface coverage increases very rapidly because coalescence has started, and it reaches eventual maximum. And then what starts is what is called as a coalescence dominated regime. Okay, where average radius goes as T⁻⁴. Generally, here growth exponent is 3 times that of the growth exponent in initial stage. Okay, and that is a bit universal. And the surface coverage saturates in this coalescence dominated region. And as one can expect, that coalescence processes rescale the pattern continuously so that it remains self-similar. Okay, then there has been few studies in the last few years that what if substrate is phase changing. Okay, not just solid or not just liquid, if it is phase changing. So, and then water vapor is getting condensed on this. Okay, so for example, there has been studies on benzene or cyclohexane near their melting points. So latent heat of condensation melts the substrate locally. Okay, and then what happens is that causes the incoming vapor or the formation of droplet. These droplet, they even start spinning while before settling on the substrate, or even they move rapidly, or they jump slightly along the substrate. Okay, so this makes the dynamics quite different from if it is substrate is altogether solid. Okay, so we try to basically come with some simulation part of this. So we have some substrate size as mentioned here. So large number of droplets, yes, 10⁵. They are placed on it, and the individual droplet is grown according to r n plus 1 or in tn plus 1 10⁻⁴. And then this is basically with consideration that, as the last line says, if three-dimensional droplets, mean a droplet is a hemispherical cap, okay, on two-dimensional substrate with contact angle very close to 90. So these are considerations before applying this particular update for the radius. Okay, and when coalescence of two or more droplets is taking place, the resultant droplet is nothing but it should be R1 cube plus R2 cube. So by mistake I have put it R2 square. It should be R2 cube plus radius of every droplet is cube and whole raised to 1/3. Okay, so this is coalescing events causes a formation of a big droplet, and it is placed at the center of mass of the coalescing droplets. Okay, so these are typical water getting condensed on a phase changing material. For example, what you see is a solid benzene at 3 degrees centigrade. Okay, so the left hand picture shows there are random jumps, and the droplets' previous positions are visible. Eventually, those previous positions imprints, they fade out, but they are visible for some time, say for a second or two. Okay, then one can see after that some experimental pictures on the water droplet on solid benzene, which is about to melt. Okay, and then there are some in the right hand side computer simulation images. So a qualitative comparison can be seen. Okay, then what happens is a comparison between normal case, means droplets are just getting bigger because new vapor is coming, plus they are getting coalesced, but there is no motion, no jump. But droplets jump when they are getting condensed on phase changing material. Okay, so one can easily see that coalescence events they get started from early time itself. Okay, otherwise initially it is T⁻⁴, and then after intermediate time it goes to final thing, that is T⁻⁴. But when their droplets are jumping, the interaction is beyond just 2 times that of radius. So it jumps, and it can cause many number of coalescence events. So the growth is quite fast.
Professor Khandkar, you have got 2 more minutes left.
Okay. So after that, we come up to what is called as what happens is that if after reaching this typical regime, because there are some experimental limitations, I am coming to that. So there are some experimental limitations that one cannot stop or control the melting of the substrate. So what will happen if to this T⁻⁴ growth law continue, whether it will continue or whether it will go into some other thing. We decided to put some parameters like and a new modality called as growth and random motion. So they will simultaneously grow plus they will go undergo some random motion also. So this was something like first of its kind, included both of them together in a model where droplets are coalescing, and then we gave some amplitude for their motion or displacement and the probability. It is found that motion in actual experimental thing, the droplets, their motion is radius dependent. It is found experimentally, so we try to incorporate that and scale the same thing using the minimum radius or radius of the smallest droplet present at time. Okay, so what is found is that this, if you see this red curve is the results from our current work, and remaining two are just the comparison for earlier established works. Okay, so this here we have found there are 4 growth regimes. There are four. Okay, so initially it is T raised to alpha 1, where it is just growing by T raised to half. Then it goes to intermediate, where it is T raised to 1, close to 1, and it is going to T raised to 3. Okay, this was a bit new kind of emergence of growth law. Okay, it was not earlier seen. And then eventually it goes to finally, and that is the classical case. Okay, so here, just a minute. Okay, so below is the surface coverage here, surface coverage. So let's see this faint blue region, which is the third law, emergence of third regime, T raised to 3. Okay, so then we try to incorporate what we'll have if we assign some probability to the motion. So it is seen that for higher probability is like no motion. Okay, and then for intermediate probability, what is seen is the regime T raised to appears. Okay, and for small value of gamma, that is probability is very high, means almost every droplet is moving. Okay, so that is recovering the standard or classical case. Okay, and then apart from probability, what we are having is if we give some displacement amplitude delta in the range of 0 to 2r, okay, double that of the radius of the droplet. So again, it is found that there is some r mu 1/8 r minimum, that is intermediate. The first thing is the classical thing. Okay, so the intermediate case where there is an appearance of some critical value of the displacement, half of the minimum radius, where this particular T raised to alpha 3 or T raised to 3 regime appears. Okay, so that is it appears to be critical value for the displacement. And for higher delta, again, there are large many coalescing events. Though coalescing events are larger, it is allowing only formation of large droplets, but then large droplets are away from each other. Okay, so they do not coalesce very easy or quickly. And again, for larger droplets, a probability of displacement is much smaller. Okay, so surface coverage saturates at that point. Okay, so I think I will come to the comments. So these are what we have studied: dynamic subbase figures on phase changing materials. Okay, a new simulation model proposed for simultaneous growth of condensation and random droplet motion together. It shows some insight into coalescing a dominated regime, where random motion induced coalescence is much faster than just if it is just condensation. And then, in addition to earlier known regimes, T raised to half, T raised to 1, and T raised to 1/3, okay, there is emergence of a new growth regime, T raised to 3, okay, which we have found in this particular case of condensation of phase change materials. I'd like to stop here. With my regards to Professor Marma and Professor Deepak. Okay, thank you.
Okay, thank you, Professor Khandkar, for the very interesting and informative presentation. Since we are running a little late, I think we can take off 1 or 2 questions. There's a question from Professor Bamma.
Yeah.
Yes.
Hi.
Please proceed.
Mahendra, classic result you quoted earlier, namely that in the coalescence regime, average R goes like T. Is there a simple understanding of that? It must be simple, but I'm not getting the hang of it. I mean, why does R go like T?
It is because basically, okay, I don't know right now the straightforward answer, but there is so much of coalescence happening, and
Yes.
droplets are just growing on their own. Okay. So, and the one thing is universal, that initial regime is here. It is just 1/3 and T raised to 1. Basically, that is for water condensation. But for other vapors getting condensed, like tin on sapphire, there is also the initial regime is, if it is Z, then the final regime is T raised to 3Z. Okay, so that is bit universal. And okay, immediately what I can think of is, there is no coalescence happening, and there are much bigger droplets, obviously, and a very small amount of vapor is getting condensed to much bigger droplets in that comparison. So they will just grow as T raised to 1.
Okay.
That's what, yeah, means. I don't know that it is a complete answer, but yeah.
Okay, later. Thank you. Thanks.
Okay.
Okay. Let's thank Professor Khandkar once again for the talk.
Sorry, I wanted to ask a question.
Yes, sir.
Yes, sir. Yes.
Yeah, so Mahendra, you said there is a regime with T cubed or T to the power 3.25. Is there any way to understand why that power is 3 or?
Yes. Yes. Okay. I haven't put that expression here, but you can have a relation between alpha 3 and alpha 2. Okay, alpha 3 is something like, okay, I don't have any in front of me. Alpha 3 is something like alpha 2 into dimensionality of droplet divided by dimensionality of the substrate. This relation has been earlier quoted in one of the references. Yes, it is, though it directly gets derived from alpha 2 itself, means growth exponents from earlier regime. But if I remember correctly, that alpha 3 derived from alpha 2 with incorporation of dimensionality of the droplet and dimensionality of the substrate, alpha 3 comes out to be 2.85 and not 3. So there is small discrepancy. So what our argument was, like, either way, we must know how the exact onset of the new regime starts. That is one thing. And another thing is, you need correction to this alpha 3 equal to alpha 2 into dimensionality of substrate and droplet. So you need correction to this, what can I say, formula itself. Yeah. So it is there.
Okay, but what's the argument that it should be alpha 2 times d by d substrate?
Oh, that, okay, right now I don't remember, basically. Okay, so basically, let me check. It is not what formula I did. Okay, alpha 3 is equal to alpha 2 into ds minus d upon g. I may be wrong with the formula, but there is some connection between alpha 3 and alpha 2. Yes, it was given by by Sons, Family, Making and Knobler's paper. Okay, I need to check. Maybe.
Okay, thank you.
I will come to a little bit later.
Okay, thank you.
Thank you.